Good evening. Today we will go into the third part of our fourth chapter, Magnetism and Moving Charges. We start today's session with the first derivation, which is motion of a charged particle in a combined field. That is, you have both the electric field and the magnetic field applied perpendicular to each other, and a charged particle enters this combined field with its velocity perpendicular to both the electric field and the magnetic field. So this is motion of a charged particle in a combined field, and this is also referred to as the velocity selector. Velocity selector. Okay, so what we have here is we have the electric field along the y-axis. So we have the electric field along the y-axis. Then along the z-axis, we apply the magnetic field. And in this, so you will see that the electric field and the magnetic field are perpendicular to each other. And along the x-axis, we have our charged particle, let's say Q, traveling with a velocity v along the x-axis. So now, as this particle enters this combined field, two forces will act on this charged particle. One force will be due to the electric field. There will be another force due to the magnetic field. The force due to the electric field, the electrostatic force, which I will denote with Fe, is equal to, as you know from the first chapter, Q times E, where E is the electric field, which is a force experienced by unit charge. So if you have Q charge, then the total force experienced will be Q times E. Now this direction of the force will be the same as that of the electric field, Q being a scalar quantity. So if your electric field is along the y-axis, then the force due to the electric field also will be along the y-axis because of this equation. Now the force due to the magnetic field is given by the magnetic Lorentz force. I'll denote that with Fm, the magnetic force, given by QVB sine theta. That is a magnetic Lorentz force. So now theta is the angle between the two vectors V and B, the cross product. So if you see sine theta, you must know it is the cross product between velocity vector and the magnetic field, which is a vector, which will give you the direction of the force on this charged particle. So V is along the x-axis, B is along the z-axis, which means we have theta as 90 and sine 90 is 1. So this will be the maximum force QVB. Now to look at the direction, remember I told you, whenever we have cross products, that is, here we have Q into V cross B. So the resultant vector will always be perpendicular to the plane containing V and B. And as you turn from V to B, if you are turning in the anti-clockwise direction, right hand screw rule says if you turn in the anti-clockwise direction, the tip will move up. That is, the resultant vector will be upwards. If you are moving from V to B in the clockwise direction, then the tip is moving down. That means the resultant force will also be acting in the downward direction. So here we see, so it's like this. You have, let's say this is the x-axis and the z-axis. We have the x-axis and the y-axis like this. So we have the electric field along the y-axis, the magnetic field along the z-axis, and we have the particle moving along the x-axis. So now the charged particle is going to experience a force QVB, which magnetic force will be perpendicular to the plane containing V and B. V is along the x-axis, B is along the z-axis. Perpendicular to that we know is y-axis, and as you turn from V to B, we are turning from V to B in the clockwise direction. So it will be downward, which is a negative y-axis. So we have downwards, we have the force due to the magnetic field. Now you will see that this particle is acted upon by two forces. One, the force due to the electric field. The other, the force due to the magnetic field, which are in opposite directions. If Fe is greater than Fm, then the particle will move up like this. If Fm is greater than Fe, it will move down. But if these two happen to be the same in magnitude, then the net force on the charged particle will reduce to 0, and the particle will move undeflected. That means it will behave as if no force is acting on it because the net force is zero. So this particle will move undeflected. So if the particle moves undeflected, we know Fe is equal to Fm, and that condition, if Fe and Fm are same, then QE is equal to QVB, from which you may write the velocity of the particle is a ratio of the electric field to the magnetic field. So that is why this is called as the velocity selector. That is, if you have a large number of particles, any particle, as you put it into this combined field, if it travels undeflected, all the particles that travel undeflected must have the same velocity, which is E by B. For example, suppose let's say we have applied an electric field of 4 Newton per Coulomb and a magnetic field, let's say for example we have 2 Tesla. Then all the particles that enter the combined field and which travel undeflected obviously must have Fe equal to Fm, which means they must have a velocity which is a ratio of E by B. They must all have the same velocity, 2 meter per second. So this is how a particle will enter a combined field. And please note, the electric field, the magnetic field and the velocity of the particle are in 3 mutually perpendicular directions. I hope you've understood how we mark Fm in the downward direction. Fm is a cross product of V cross B. So V along the x-axis, B along the z-axis. Perpendicular to that force must be along the y-axis, but negative y-axis, because as we move from V to B, we are moving in the clockwise direction. So this is how you will show clockwise direction and the tip will move down. Okay. So we will now move on to the next topic, that is force on a current carrying conductor when it is placed inside a magnetic field. So we are now going into the next one, force on a current carrying conductor when it is placed inside a magnetic field. This I think you have done some little bit of this in 10th standard. Current carrying conductor placed in an external field. In an external magnetic field. Now please note that we have written here external magnetic field, because when we did the last session, when we did Ampere's circular law, you would have noticed that for a current carrying conductor like this, which is carrying current, it has its own magnetic field. Let's say at a point R from the conductor, we derived B equal to mu 0 I by 2 pi R. This is from the last session, Ampere's circular law. So every current carrying conductor has its own magnetic field. What we are now going to do is, we are going to keep this conductor in an external magnetic field, some other magnetic field, and we are going to keep it in that external magnetic field. That's what we are going to do. And then find out the force experienced by that conductor. Now here we have the conductor like this. I'm going to draw the conductor like this, whose length is L and the area of cross section is A, and we are now connecting to an external cell, so that every electron here is going to now travel towards the positive terminal. So we have the drift velocity of the particle in this direction. But because the electron is moving in this direction, you will take the current to be in this direction. Okay, opposite to the direction of motion of the electron. Now this conductor with lots of free electrons which are able to conduct electricity, we are now going to place in an external magnetic field. I just drew a random direction. The angle between I hope you remember, I told you already in this chapter, length is taken as a vector quantity and the length is taken in the direction of current. So this is the direction of length, this is the direction of length vector, this is the direction of current. Length vector is always taken in the direction of current. So now theta I am going to define as angle between the length vector and B. So we have this here. Okay, so the electrons will move towards the positive terminal of the battery. Now, every electron is going to experience a force given by Lorentz magnetic force. Because what is Lorentz magnetic force? It is a force experienced by a charged particle when it is placed in a magnetic field. Now this conductor has lot of these free electrons, and each of these free electrons are moving inside the magnetic field because we have placed the conductor in the magnetic field. So each electron is a charged particle moving inside the magnetic field, which will therefore experience a force given by Q V B sine theta. Let me call this force as small f. That is force experienced by each charged particle. Now I replace Q with the electronic charge E, and I replace this velocity with Vd, because if you remember from current electricity, the velocity of an electron in the presence of an electric field, that is when it is connected to a cell, the velocity with which it moves towards the positive terminal of the battery is what you call as drift velocity. So I am placing here as drift velocity B sine theta. Theta will be the angle between velocity and B vector. Velocity I have shown like this because it is an electron. A positively charged Q particle would move in this direction. So theta is the angle between velocity and magnetic field. Now the number of electrons. So this is a force on one electron. Let's find out how many electrons are present in this conductor. I hope you remember that we defined the small n as number of electrons in unit volume of any conductor. This we did in current electricity. When we did that I equal to NEAVD, I told you n is the number of free electrons present in the conductor for unit volume. So if you want to find the number of electrons, we just need to do number of electrons equal to this n into volume. Volume of a cylindrical wire or conductor will be base area into height, which is A into the length L. So this will be N into A into L. Volume. So now we have the total number of electrons. We have the force experienced by a single electron. So the total force experienced by the whole conductor will be number of electrons multiplied by the force on each one. So this will be N into A into L E Vd B sine theta. And from current electricity we know N E A V D is what we call as the current. So we may write this as the current I into L B sine theta. Sine theta tells you that it is a cross product between two vectors. The vectors being the length vector in the direction of current and the other vector is B. Theta is the angle between the length and the magnetic field B. So combining that, you may write the force experienced is equal to I into L cross B. These two are the vectors and F is the resultant vector. Now the theta angle is the angle between L and B. So obviously when will you have maximum force will be when theta is 90. Theta 90 would mean you have your conductor like this. Magnetic field is perpendicular to the conductor, and when theta is 90, you will have maximum force acting on the conductor. But if your conductor, let's say the current is in this direction, magnetic field also you are applying parallel to the length of the conductor. It does not experience any force because theta 0 would mean sine 0 is 0, no force. Even if you are applying, let's say magnetic field is in this direction, but the current is in the opposite direction. So length vector is in the opposite direction. Then theta will be 180, sine 180 is also 0, force will be 0. Another important thing is to note the direction of the force experience. Force experience is given by the cross product. Cross product, what does it tell you? The force vector will be perpendicular to the plane containing L and B. And as you turn from L to B, if you are turning in the clockwise direction, for example, let's say L is along the x-axis and B is along the z-axis. Then X and Z perpendicular to that you will have the y-axis. So force will be along the y-axis. Since you are turning from B to B in the clockwise direction, the force will be along the negative y-axis. On the other hand, suppose you had velocity along the z-axis here and the B along the x-axis, then V to B would have been anti-clockwise and the tip would move up. That means the resultant force will be acting in a direction perpendicular to the plane containing L and B, but in the upward direction. You can also get the direction using Fleming's left hand. Fleming's left hand rule tells you that this is the direction of magnetic field. Your forefinger gives you the direction of magnetic field. The middle finger will give you the direction of current, and the thumb will give you the direction of force. So here, if your magnetic field is like this, see, your magnetic field is given by the forefinger. Here, this is a current direction. So this is a plane containing I and B. So your force will be perpendicular to this plane containing I and B, L and B. So this is how it will be, and your force will be in this direction coming out. Okay, because L is like this, B is like this. This is B and this is your current, and this will be the force. If you're using cross product, you see the plane of the board is the L and B. So naturally, perpendicular to the plane of the board must be the resultant vector. And since you move from L to B, as you move from L to B, you are moving in the anti-clockwise direction. So you will see your vector will be perpendicular to the plane of the board and coming out. So whether you are using this cross vector product direction or Fleming's left hand rule, you will still get the same direction for the resultant force. So that's the second topic for today, and we have one more topic for today, which is force between two parallel conductors kept close to each other. Force between two parallel conductors kept close to each other, kept at a distance d. Okay, so we have the next topic, force between two parallel conductors carrying current. Okay, so let's look at this. We have one conductor here, I'm going to call it as the first conductor, which is carrying a current I1. Okay, and then parallel to that I'm keeping the second conductor, which is carrying a current in the same direction, that is I2, and the two are kept at a distance small d. Now let us look at the force between these two. Because they are carrying current, naturally they'll exert a force on each other, and that is what we're going to derive. In Ampere's circuit law in the last session, remember I told you every current carrying conductor has a magnetic field. This is from the last session. Okay, every current carrying conductor has a magnetic field at a distance r, and that is given by the formula mu 0 I by 2 pi r. And the direction of that magnetic field is given by the right hand thumb rule, which tells if you hold your conductor like this, the thumb in the direction of current, then the curling of the fingers will give you the direction of magnetic field. So if I have a conductor like this, curling, when you look at this, it's a circular loop, the magnetic field. So on the right side, you will see it's going in, tangential and inwards. So perpendicular to the plane of the board and inwards. As you come out, here it's turning and coming out. So it will be tangential and perpendicular to the plane of the board, but it will be coming out. So if I am going to mark the magnetic field for this one, on the right side I would mark like this, showing you that it is perpendicular to the plane of the board and inwards. And on the left side I would mark it like this with a dot, showing you that as you curl your fingers, here it's going to come out perpendicular to the plane of the board. So that is the right hand thumb rule, which gives you the direction of magnetic field for any current carrying conductor. So let us look at this first one. This first conductor is carrying a current I1. So naturally at a distance d here, it must provide a magnetic field. And with the right hand thumb rule, this thumb showing you the direction of current in that conductor. On the right side, the magnetic field is going to go in, and on the left side, the magnetic field is going to come out. So here, because of this conductor carrying current, there is a magnetic field which I'll show you like this. because you see it's going in, and that magnetic field I will call as B1 because it is due to the current I1 in conductor 1, and that by Ampere's circuitry law is mu 0 I by 2 pi r, where this I is I1 because of this current and it is at a distance d. Okay, so it is at a distance d. Now because of this conductor also there is going to be a magnetic field. So if I hold the conductor in my right hand, the thumb giving you the direction of current, on the right side it's going to go in, but on the left side you will see it's coming, curling and coming out. So because of this current I2, there is going to be a magnetic field here which I will represent with a dot, and I will call it as B2 because this field is due to this current carrying conductor. And I hope you understood that on the right side it's going in, curling and going in. When I come to the left, it's going to come out. That is why I marked it with a dot. So if I write the expression for B2, that will be mu 0 I2 by 2 pi d itself, because we are from this conductor at a distance d, we have marked B2. This expression is from last session, that is Ampere's circuitry law. Now you will see that this conductor, its own field is B1, but it is placed in an external field B2. So every current carrying conductor when placed in an external field will experience a force. We just discussed that, and that force experienced by the first one, F1, formula we just derived ILB sine theta, where this conductor is carrying a current I1. The length of the conductor we have taken as L, and it is placed in an external field, which one? B2. So B2, please note the difference. B1 is its own field, but we are talking about the external field in which this conductor is placed, that is B2. Theta is the angle between the length and magnetic field. The length of the conductor is like this, but the magnetic field you will see is coming out like this. So length and magnetic field are making an angle of 90, and so this will be sine 90, which is 1, and I will substitute now I1 L mu 0 I2 by 2 pi d, which is B2 from here, mu 0 I2 by 2 pi d. If I rearrange it, I will get F1 equal to mu 0 I1 I2 L by 2 pi d. Okay, so that is the magnitude of the force experienced by the first conductor when it is placed in the magnetic field provided by the second conductor. Now this force has a direction which is given by Fleming's left hand rule or L cross B, either one you can do. Let's look at Fleming's left hand rule. Now this is a magnetic field, this is a current, this is a force experienced. Your magnetic field tells you it's coming out. So I have the current is moving up. Can you see? The current in the upward direction. The magnetic field is coming out like this. The force will be to the right here in this direction. I hope you can see that. This direction of current in the upward direction given by my middle finger here. The magnetic field you will see is coming out because your magnetic field, external magnetic field is coming out, and this will be the direction of force experience. So that's why I'm going to mark this force as F1 to the right side. Now I'm going to look at the force experienced by this conductor, the second one. The second one I will write as F2 will be, again formula is ILB sine theta. Current carried by this conductor is I2. Length we have taken same for both the conductors. But its own field is B2, but it is placed in an external field which is B1. So this will be B1, and here again will be 90 because length of the conductor is like this, but your magnetic field is perpendicular and into the board. So like this. So it will be sine 90, and sine 90 will be 1. So substituting I have I2L mu 0 I1 by 2 pi d. That means I have substituted for B1 from here. Rearranging, I have F2 as mu 0 I1 I2 L by 2 pi d. So you will see both F1 and F2 are equal in magnitude. Let us look at the direction. Again, remember, this is the magnetic field, this is the current, and this is the force. Here the magnetic field is going in. So I have shown my forefinger going inwards. The middle finger is going upwards. So the thumb is to the left and that will be the direction of force F2. So you will see now these two forces are equal in magnitude but opposite in direction. So this is analogous to Newton's third law, which says every action has an equal and opposite reaction, because this is exerting a force F1, this is exerting a force F1 on this, and this is exerting a force F2 on this. They are equal and opposite. Okay, now from this we need to know how to define 1 ampere. Okay, so in 12th standard you will need to know how to define 1 ampere using this concept. Let's see how we can define 1 ampere. The force formula I am rewriting here, F by L, which means I have brought this L to the denominator on the left side here, will be equal to mu 0 I1 I2 by 2 pi d. Right. So F1 and F2 are the same. So force per unit length on either of the conductors will be mu 0 I1 I2 by 2 pi d. Now, so we are now going to imagine that there are two conductors which are placed close to each other. That is, two conductors like this. Both are carrying 1 ampere. Okay. And both are placed at a distance of 1 meter in air or vacuum, which means if I am going to substitute here, in air or vacuum, mu 0 value is 4 pi into 10 raised to minus 7. I hope you remember. I told you in the beginning of the chapter, mu 0 by 4 pi is 10 raised to minus 7. So mu 0 will be 4 pi into 10 raised to minus 7 into 1 divided by 2 pi, and d is also 1. So if I cancel this, I'll see this is equal to 2 into 10 raised to minus 7. Force per length will be Newton per meter. So you may define 1 ampere current as that current which, when flowing through two parallel conductors placed in air or vacuum at a distance of 1 meter, experiences an attraction or a repulsion equal to 2 into 10 raised to minus 7 Newton per meter. Let me explain that attraction or repulsion. You just saw that when the two currents are in the same direction, F1 and F2 were like this. So there is an attraction when they are in the same direction. Suppose the currents were in opposite direction, you may apply Fleming's left hand rule and you will find that F1 and F2 will be repulsive. Okay. So if the currents are in the same direction, the force between them is attractive. Otherwise, it is repulsive. So that is why when you define 1 ampere current, you will say 1 ampere current is that current which, when flowing through two parallel conductors placed in air or vacuum at a distance of 1 meter, either experiences a repulsive force or an attractive force equal to 2 into 10 raised to minus 7 Newton per meter. Right? So this is how you will define 1 ampere current. So today's we had 3 derivations. We started with the velocity selector. Then we did I B sine theta, that is force experienced by a current carrying conductor. And along with that we did the force between two parallel conductors carrying current. Okay. Thank you.